want to do another example of connected graphs, and I'm actually going to take the opportunity to show you something a little different in terms of using R that some of you might already know, but just in case, something which in a way I would probably accept as another alternative to Jupyter notebooks in terms of your solutions to problems. Okay, but before we get to that, what I want to do is spend a little time again on how to import data and so on. And that's a running theme in this course because I think it's quite important. I think as data scientists, this is something that people do often. And I think it's worth spending some time on this because it's very easy to work on basic problems like we have in the written part of the assignments, for instance. But if you're confronted to real life problems, then those problems are typically much bigger. And it is worth seeing what type of problems arise when you're dealing with such bigger problems. And okay, I've got my timer there, I've got a laptop here, and I've got that one I won't use, and I've got my screen there, so I'm going to be going back and forth between the various places, and I hope it doesn't get too disconcerting. But okay, let's get started. So what I want to go through are two examples for now, and we'll do more later, of connected graphs. And somebody asked me recently, like, how do you determine connectivity? And well, if you, there's several ways. If you're doing it by hand, typically you would do it visually. You look at a graph and you look at if it's possible to go from anywhere to anywhere else. Strong connectivity is going to be a bit harder to determine because you're following arrows and not edges, and so you have to follow arrows in whatever direction they are going in. But it's still quite a relatively simple problem if I give you a graph with 15 vertices. But what happens when you have a bigger graph? You can find a lot of graphs online, and I'm going to show you, show you a few examples of graphs. So it's interesting. I don't know if the image is going to disappear. I've been bugging with my computer for some time. It will not have a screen turn off, and it turns out that, of course, it turned itself off. Never mind. So there's a bunch of data sets. You should be seeing this. For example, Stanford has a collection of data sets that you can take a look at. We're actually going to use two of the graphs that they provide here. There's a variety of things, and we will look at other examples further down the line. And what I'm going to do is I'm going to start with this one, which deals with social circles on Facebook. I'll admit right away that I don't have a Facebook account. I have not a massive clue about what's going on there. But as all social networks, essentially this is organized by saying, oh, so-and-so is my friend, and etc., I believe. I study networks. I don't partake in them. So what you see is this is a network with 4,000 nodes, sorry, about 88,000 edges. And I'll point out that actually this is not true. The network we are going to look at is much smaller than this. It is a group of networks that in total have this characteristic. And I'm not going to deal into this way more in this data set than what I'm going to be using. I just, to start with, want to spend a little time on just how to deal with this. So you can see that right away they're talking about connectivity. WCC would be the weak connected components, and SCC would be the strong connected components. So they're counting how many of them there are in the network. These are things we will see later. Okay, for now I'm just bothering about how to load the networks and how to do basic things on them. So that's what we're going to be using. Now, when you load the data, and I will give you some of that data. That one is not too big. So what you get is for a given, so there are something like 9 what they call, what is it, a node ID, I believe, which I think is someone. That description, you'd get some details here. I haven't read this yet. The description here is not super detailed. Never mind. So based on a node ID, we get a bunch of files. So one has the edges. One has the circles, which we're not going to use yet, but we might use in a later life, let's say. And then there are features, which, if I understand well, the description here could be something like political. So this is if you want to add more components to your vertices, okay? Because the vertices are people, and so they will be showing some opinions about things, or they will be liking some things, and this is apparent in the data set, but we're not going to use that this far. I think the ego user is actually the root, essentially, of the graph that they're looking at here, and the features for the ego user and the feature names. So, but as I said, we're going to be focusing only on those two, and as a matter of fact, mostly on the edges. But as always, as I point out, it's interesting to know how to do things, and therefore I'm going to show you how to do some processing. So I'll read in, so I'll distribute these two files. I'll read them in. Their tab separated value, well, one of them is tab separated, the other is space separated. So that's how you would read them. Okay, you could just say the separator is a tab or the separator is a space. There's no headers in those files, and when we run this, we get the following. The circles, I'm showing you everything because we have a problem with circles. If you look at it, maybe I could look at the original file. So you can see that circle 15, for example, that's where you see that it's a tab separated, by the way. This is showing you tabs. Circle 15 is very long. And what's happening when we look at circle 15 here, this is one column. So it hasn't considered that these subsequent rows are actually the same row. It has just stopped at 21 columns or something. Yes, 21 columns. That's not great. The edges seem to work fine. Okay, this is just the header of the first 6 rows of the edges, and V1, V2, and we get a bunch of things. So for circles, I'm just going to show how to do things. What we seem to be running, and I tried other functions to read in this file here. We seem to be running with into problems. I don't really understand why, but you know, like when something refuses to give, try another way. And in this case, what I'm going to do is I'm just going to read every line in the file and process it. And so to do that, I define a function, and I typically quote where I find functions when I use something specific. I've defined a function that I've adapted from something here, which it must be on Stack Overflow, yes. And what it does is it processes a file. You give it a file path, that's a file name or a file path, and it creates a file connector. And then what it does is it reads every line. And while it can, okay, this means if I've got to the end of a file, I'll just stop. But while it can, it reads a line, just a single one. What it does is it puts line in the output and then just increments this. And so when you do this, you end up with a bunch of, so it's a list, okay, I'm creating a list. You end up with a list of stuff that looks something like this. To process this, which I could do in here, okay? Here I'm not bothering with it. What I can do is I can simply substitute a comma for every tab that I get. And when I do that, I get something good, which I should actually illustrate probably with the one that's messing up, which is the 15th row, I believe. So let me control enter, enter. I don't need this one, but I do need this one. And then if I do circle of 15, I think I said, no, was it 15? Or maybe I'm missing one. Ah, circle 0. Okay, it starts at 0. So 16. So you can see that what we've created at this point is just a list of tabs. And if I now process it properly, then I get a vector with these entries. Now, okay, I'm going to use iGraph as we've done before. And what I'm going to do is I'm going to read the graph from the edge list. And so the edge list has to be from to if it's directed, or arc edge involving these two vertices if it is undirected, as this one is. By the way, I didn't show you, but here it says, where is this? Blah, 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 somewhere there. I don't remember where it says this, but it says that the Facebook data that they have there is undirected, whereas they have Twitter and Google Plus data, and that one is directed. So we make it undirected, and that just requires to, of course, I need to load the file. I get this graph. Now, that graph has 347 vertices, and it has 19 connected components, and you could see that. I mean, that guy here, 15, is clearly isolated, this one too, those probably are, etc. But all of this is nicely connected, and as a matter of fact, there are 19 components, and if I look at the component size, which is an output of components, one is 324, and the others are these small components, okay? Now, I want to keep only, this is something you'll do quite a lot, want to keep only one of the connected components. In this case, I want to keep, so here I'll just show you when I run groups of the connected components, what it does is it gives me a list. It tells me it's a list in which each of list entries contains the vertices, the index of the vertices that are in that connected component. So it turns out here, that one is listed first. There's no reason for this to happen. So again, it's one of those things where it's good to change tags sometimes. And let me, for example, say I want to keep the largest connected component. Well, what I can do is if I use this function here, it's going to tell me the length of each of, it's going to apply to the list groups of C, the function length. So it's going to return the length of each one of those list entries. And what I'm doing is first I'm unlisting so that it makes a vector with this, these values. And then I'm saying, well, which one of those equals the maximum of the component sizes that we got from here. So which one has 324? So that's if you want to select the largest, that's how you would do it. And if you do this, then you get or in this case, it's the first one. And now I'm going to select a subgraph. Well, it's called Induced Subgraph. That's the function to make a subgraph, and it's a subgraph of G. And what I'm saying is, well, in groups of C, get me the vertices that are in the index of that component that we identified as being the largest. And when I do that, well, I've got rid of all the vertices that were not in that that component, sorry, and that's what I have. And actually, I probably could add something here. Let me just I could say, what is this component connected? I've called it G underscore C. And when I evaluate this, true. Okay. Whereas if I did this with the original G, I would, of course, get false, I hope. Yes. Okay. Now, I want to do another example that's bigger. So on this thing here, I think it's on this one. Yes, Twitch. So that's another thing that I don't use, but I'm more aware of. Twitch is something where gamers show their games, I believe. And so there's data here on Twitch, and you can see it's got 168,000 nodes and 6 million something edges. It is undirected. Okay. So just in passing, we'll load it from a zipped file because the file is quite big. I believe even if you look at the zipped file, yes, it's 26 megs compressed. So it's a big file. So what I do is I keep it zipped. And so this is a way that you can use to unzip on the fly, let's say, a file. So I'm saying unzip this file, make it into this file, and read this file. Okay. So what we get is something that looks like this. These are pairs of vertices. So these define an edge. And if I look at the dimension, I do get almost 6.8 million lines. So this is getting substantial. That's bigger. And when I try to do this, I run into a problem because the first thing that happens when you try to load the graph is that it complains because some of the vertices in this list end up having the index 0. I'm not entirely sure if they meant it, or I think it might be, actually thinking about it, it might be that I simply need to shift the indices by 1 because clearly from what we were looking at here, they seem to be using the usual C and sort of descendant languages convention that counting starts at 0. So I'm guessing, I just realized this, that I probably could just shift everything by 1 and get something where I don't have 0 vertices, because apparently graph from edge list doesn't like 0 vertices. But okay, suppose you want to remove them. This is how you would do. I just find, and I want to show you this one because I think it's quite important to see how to do that. So I have 2 columns. And when I'm looking for indices of entries where I would have a 0, I could have zeros in the first column or the second one. One way to do it, and actually seeing the time, it won't be this time, but in the next video that I'll post right after this one, but which will be for after the holiday. So in another way, I'll show you another way to do this. For now, I'm just going to say, if you do it like this, hopefully this should... Ah, yes, of course, I didn't load the Twitch thing. And you'll see that Twitch is that big database. It's going to take some time to load. And that brings me to the next issue. So that's it, it's loaded. So when I do this, I should now have removed the rows that have 0. Just in passing, so in the future, what I will do, in fact, is probably just shift things by 1. Actually, I have a minute. I don't know if I can install this in a minute. Okay, no, I'll do it in another video. So what I wanted to say, now if you try to load this, it's not working. And I think that's one of the problems with syzyg. Each one, every time you connect, it tells you that your virtual machine, or it's not called a virtual machine, but that's essentially what it is, your instance or your kernel instance hasn't been loaded, is not running. I think each of these kernel instances are quite small. And so, well, they're attributed a low memory amount. And so I ran into issues running this. I crashed my kernel many times, tried to resolve this. And so I'm guessing, yes, it's a RAM problem. And so what I'm going to do, and as I point out, I think we're out of time, but it will be the first video for after the break, but I'll point out that some of you might be interested to look at. So what I'm going to do, instead of using this approach, I'm going to show you how to do things directly in R, but I am going to try to do the same type of thing as we're doing here. I want something interactive and where you can also produce a document that looks nice and that mixes code and running. So I am going to give you a very brief introduction to R Markdown, which is very similar to Jupyter Hub. Okay, and I will do that, as I said, in the next video.